So folks, Alex here. So today I really wanted to continue playing with this no std no main shenanigan, right? And as you probably remember, the last time we managed to create ourselves a bunch of little kind of crappy utilities that don't use the Rust standard library, right? So I guess the kind of more interesting one of those was this kind of cat utility from GNU Core Utils reimplementation, right? So yes, we in fact can like concatenate a bunch of files, right? So cargo toml, cargo lock, and here you can see that yes, these two files are concatenated and printed to the console, right? And the challenge here, of course, like the whole point of that exercise is that like we suppose not to use the standard library, right? And thus no std no main. And as you can probably tell, we needed to like reimplement a bunch of stuff, from scratch using raw assembly basically. So today the goal will be to play around with something like a little bit more tangible, maybe create like a simple memory allocator in that like no std universe, right? And what's interesting about that is that we can actually use it then with ld preload or something, right? With ld preload and then the program name, and thus the kernel loader that loads your program will tell the dynamic like shared object loader to kind of prioritize the shared object that you provided over something else, and thus you can basically like substitute your like memory allocator or something like that with your own stuff, which is kind of useful for debugging and like experimenting and all that. So we'll try to build our simple memory allocator as a shared object, right? And then using the ld preload, basically try to preload it into a bunch of existing utilities and see how it performs. So something like that. So cargo new lib allocator something, right? And let's see, allocator like lib crate type. What's the crate type? It's cdie-lib, I think. Right, so we are telling it that it will be a dynamic object, so .so on Linux, but also gonna be like C compatible, right? So something like that. I think here we want something like workspace, and then like members, and then like allocator, something, right? So here, so let's maybe like steal a bunch of stuff from here, like that. By the way, so here we have an edition 2024. Okay, probably not gonna be too happy about some of the stuff. Yeah, so this, right? So I think let's substitute no mangle with no mangle, replace, right? And what else? librs. Okay, so now it's happy. So what do we need here? Make no mangle. We don't need these. Let's keep this. We don't need that. We don't need to close and exit. Let's keep the print string and error string, although, okay, fine. Render usize, why not? Print usize. I don't think that we need that symbol. And let's keep that symbol, okay. So, cargo check. Supposedly it compiles. Let's, you know what? Let's maybe potentially create like a simple, just test function or something like that we can try out to load from, I don't know, from Python or something, and see if if it compiles properly. So it's like print, I don't know, hello world or something, right? And print string, like hello world /n, right? So extern C, let's say that this is unsafe as well. Do we need to tell that it's public? Probably not, but you know, print hello world or say hello. Okay, so cargo clean, right? Cargo build. So the question, do we get the shed object? We don't. Cargo build package allocator, maybe? Still not getting the shed object. Clean. And give me allocator. Where's my allocator? Okay. liballocator.so. Okay, so target, debug. Let's open Python. Let's import C types or something. C types. CDLL. What is it? liballocator. So, and that would be like L equals to this L, and the name was say hello. Say hello. And yes. So as you can probably tell, you know, the function that we created here, you know, it actually been exported, and we can actually like use it from Python, for example, if you care about those things. This is goes to the saying that, you know, it's super easy to integrate Python with native code. It is super easy. So yeah, so this function, right? But we don't need that, of course. We need malloc, right? So in order to create a memory allocator, we need to kind of support at least malloc and free. Calloc, I'm not sure. I think calloc can be omitted, and I think realloc is kind of useful for many purposes as well, right? So let's say that we have like malloc, and supposedly malloc takes like size is usize, right? So if extern C malloc size usize, and supposedly it should return this like mute pointer to U8, right? And who knows how it's implemented? Like certainly not me. The other thing would be like free, right? So free takes this PTR, which is a const pointer to U8, and does something, right, to free it basically, right? And I think we will be needing another symbol which is called realloc. And realloc does what? So it takes a pointer and the size, right? And basically the idea here is that if we already have like a pointer to memory that was allocated by malloc some time ago, right? We can try to, you know, like change the size of that allocation, and typically, you know, like reallocate a bigger buffer, copy that stuff over from one place to another, and free the previous buffer, right? Something like that. So the pointer and size. So pointer, I think it's const pointer, and size, it's like new size basically. usize, right? Okay. So now the question, how do we malloc stuff, right? How to even start allocating any memory at all, right? And the key idea here is that all your memory belongs to kernel actually, right? So the way allocation works is that you go to the kernel and just ask the kernel to map a bunch of memory pages, you know, from its space basically to your process, right? And now like those memory pages, you know, a discrete amount of those new memory pages become available in your process. And this is basically what memory allocation actually is, right? The difference between like different memory allocation strategies and whatnot, right? The reason why, I don't know, memalloc and gmalloc or something like that, the reason why these two different is that, you know, it boils down to the algorithm of how do you manage that that mapped memory, right? But the kind of core idea is still the same, right? You just go to the kernel and ask some memory from it. And the way it works, right, at least on Linux kernel, and like my only concern is Linux, you know, I don't care about Windows or any other operating system, is that we have this mmap system call, right? And right, so we will be needing to call into the kernel. The way we do that is using that. So malloc, right? Let's say it's ptr. Okay, so the way it's implemented is this. Or maybe we're supposed to read the manual, maybe. So map, right? See, I mean, memory map does a lot of things. So you can, for example, back up your memory with a file or something like that. We don't care about all those scenarios. The only thing we care about is that scenario where we're just asking for some memory, right? So let's see. The way you do it typically is this. You would provide it with some len, right? So how many bytes you want the kernel to provide to you. You would ask it for a memory prototype. And I think memory prototype is like, you know, like, is it readable, writable, that kind of stuff. You would provide it with flags. Flags are basically, you know, what kind of, you know, type of memory that is. Is it like, you know, file-backed memory or anonymous memory, or like how you supposed to manage that memory, right? If it's file-backed, then you need to provide a file descriptor, right, that you obtained by opening a file, you know, previously. And what is this? This is offset. So basically, you can map a file into your basically take a file and map it as memory into your process, right? And you can like provide an offset to that. But this is also not something that we're interested in, right? So let's just go ahead and try to implement that. So the system call number is 9. Oops, is 9. 9, please. Okay. Then RDI long address. RDI is 0. We don't care about any addresses. RSI is len. So malloc RSI is len. And this is basically our size. RDX is prototype. Okay, so what is prototype? Prototype exec read, write, and none. Yeah, so you can tell if that memory will be like executable, readable, or writable, right? So executable, for example, is something that just-in-time compilers need, right? So just-in-time compiler, as a part of its, you know, job, it creates this like, you know, binary representation, like machine code basically on fly, right? And in order to make it executable, it needs to like allocate a bunch of memory on heap, place that machine code into that heap, and mark that memory region as prototype executable. Otherwise, the CPU will, you know, basically, you know, refuse to execute it. But we don't need that. We need only prototype read and write, although I have no idea what that is. So grep prot read, I guess. Minus ri user include or something, right? So yeah, so you know what? I'll do this. Define. Right, so prototype read seems to be just 1. So, and I think we need prototype write. Is just 2. right? So RDX is our prototype, R10 our flags, so R10. Okay, so what kind of flags we have? Flags, so flags. Okay, so I think we need map private and also map anonymous, right? Because, you know, we are not backing our memory up with a file. So map private map private is 2 R10, and then anonymous, right? Anon. Oh, map anonymous. Map anonymous seems to be 20. So this is R10 flags, right? R8 is file descriptor. So R8 is a file descriptor, which will be -1 if if it's anonymous, right? I think it should be so shared anonymous. Mapping is backed. The FD argument is ignored. However, some implementation require FD to be -1 if map anonymous or map anon is specified. So we'll just use this -1 thingy. And the offset is 0 because we don't give a shit about the offset, and it's R9. R9 is 0. So these are good. RSI, one of these. Course, bytes written. PTR. Although, yes. Well, you know what? This could have been just a mute pointer to U8, right? But this, yeah, something like that, right? It's supposed to work. So this is malloc, right? And then for unmapping memory, it's a good question, right? So the C library, like the interface that it's actually looking for, would only require the pointer, right? But the problem, I think, is that if we were to use memory unmap syscall for that, it actually asks for a pointer and a size, but we don't have a size anywhere. And I think for reallocation, we also need, you know, we need to know what size it used to be, right? Which is kind of a little bit problematic, I think. But, you know, let's try this out nonetheless. So let's say for freeing we do nothing. Let's just leak all the memory, and maybe let's print string something like, I don't know, allocating, and let's maybe print usize like size, right? And then let's do something print string. Maybe here. Something like that. Let's print out the PTR that we've gotten as usize, and let's print out the /n, like finalizing /n. Okay, so cargo built, it builds. We get this lib allocator here. Let's try to do this. Let's say we have this LD preload equals to target. Oh, we are already here. You know what? I want this. So let's say we have this LD preload equals to target debug lib allocator dot so, and let's do ls, right? supposedly we should print some strings here, right? LD preload equals to this, and we're not getting any prints actually, right? Why is that? Okay, LD preload cannot be preload, cannot open shared file. Okay, why is that? Target debug. Okay, cargo build cannot be preload. Cannot. Lib allocator. So should be there, right? Debug. Oh, I see. So I think it's like package allocator. This is kind of confusing. Where's my shed object? All right, so now it works. This is kind of confusing, not gonna lie. So at least we are allocating something for sure. We are allocating something. So allocating print, we do this, we do that. Let's maybe disable this. Let's rebuild and let's share. Okay. So now it works. Now it works. At least it prints something, and it seems that we are getting all the way to the output of that utility, right? So it prints allocating, a bunch of bytes, and here's address, and let's maybe print when we are freeing or something like freeing. And print usize ptr as usize and /n at the end, something like that, right? So this is freeing. Let's build. Let's run. Okay. So we're allocating, we're freeing, we're allocating, we're freeing, and all that. So I guess the problem, I mean, it already kind of works, right? Problem with that implementation is that freeing doesn't actually free anything. So technically we're supposed to, call this memory unmap thingy, but there is no way we can safely call into it because we don't know the len of the allocation. All right, so how do I know the len of the allocation? So technically, like in a decent allocators, right, they maintain this like static state, right? And maybe that state represents like a, like a link, like doubly linked list of like allocations or anything like that. We're not going to be doing that today. I think what I want to do is I want to tag every allocation with size tag, basically, right? So instead of allocating the size, I want to allocate something like core mem size of usize thingy, right? So now I have like more actually than being required. Here I actually want to add like 8, right? So I want that those first 8 bytes of the allocation to be mine, basically, right? So because I want to store a header that describes that allocation in those 8 bytes, right? And unsafe. I mean, it is unsafe. What if I say unsafe here and still doesn't want that? So let's maybe allow, what is it, unsafe op in unsafe function, right? Okay, and pointer is a pointer to U8, which means that add actually will give me 8 times 1, right? Which is kind of important. Okay, so I'll give this add plus 8 actually. And within those first 8 bytes, I want to store the size, right? So let's say I have this pointer itself, right, as like mute pointer to use size now, right? Let's dereference it and let's just write size into it. So now I have, like, I'm prefixing my actual allocation with unsafe public. Wait, what? What is it? Malloc unsafe. Public unsafe. Is it public unsafe or unsafe public? Public unsafe. Yeah, like that. Okay. So, yeah, I'm prefixing it with this. When I'm freeing, I need to now remember that the pointer that I've gotten is actually that pointer, right? Which means that if I were to run unmap, which I need to implement as well, right? So RDI RSI, let's say we have this, so free, right? So the syscall number is 11, I think, right? 11, but then RDI is address and RSI is LAN. So RDI is address, which is actually PTR substitute 8, right? So this is address, but then LAN is PTR substitute, or I guess as const use size, right? We take this, we substitute 1 from it, we dereference, we get the allocation size, and we need to add 8 to it. We don't need those, right? PTR cannot be assigned. Okay. Yeah. PTR. Yeah, we don't need that. So RDI is address and size LAN. Will that work? Yeah, place your bets. Will that work? So we substitute 1, we take the LAN in bytes, we take it, we add 8 to it, we get something, and we are calling unmapping on it, right? Which should work, I think. Let's see. All right, so now it's segfaulting. Oh, and it's segfaulting because of the null pointer. So if PTR is null, actually, then we just return. So why? Because C is garbage. That's why. Yeah, C is garbage. So, okay. So we're allocating and we're freeing, nothing segfaults, right? And I think we need to do the reallocation bit as well, right? So what is reallocation? Let's see what is reallocation, I guess. And it's not 2. So realloc. So what is reallocation? Function changes the size of the memory block. The content of the memory will be unchanged in the range from blah, blah, blah. If the new size is larger than the old size, the added memory will not be initialized. So yeah, so basically everything boils down to what? Nothing wrong. Technically speaking, we should be able to, you know, change the memory allocation size in place, basically, but we're not gonna be doing that, right? We're not gonna be doing that. Instead, I think we will be doing the following. So like let new allocation, like malloc, with this new size, right? And then we basically need to copy over stuff from like the old pointer to the new pointer. So let old size is ptr as a const pointer to your size, right? Let's substitute 1. Let's take this. So that's the old size, and then 4 offsets in from 0 to like new size min old size, and then core ptr copy non-overlapping from source. The source will be what? ptr, right? Yeah, ptr. Destination will be this new allocation. And oh no, we don't do that actually. Wait, copy non-overlapping. We just, yeah, just basically say this. So it's like new size min old size, right? But yeah, it's not in cycle actually. And for the result, so what does it return though? Realloc returns a new pointer, right? So it returns a like mute pointer to U8, and that new pointer to U8 should be this new allocation, right? And the old allocation should be freed, right? So it's like free ptr, right? Kind of like that, but it's not all, right? Because again, C is garbage, right? So the content la la la, and I think this function has some kind of corner cases, I would say, right? So if pointer is null, then the call is equivalent to malloc size for all values of size. If the size is equal to 0 and p is not null, then the call is equivalent to free actually, right? Okay, if size is equal to 0 and p is not null, okay, which means that if this ptr is actually not null but size is 0, it should act as a free function, right? So if like not ptr is null and new size is 0, then we kind of just free the pointer, right? And we return the pointer like that. Yeah. And yeah, as mute pointer to U8, right? And yeah, something like that. So build package allocator. Okay, segmentation fault now. All right, I think I figured it out. So have I mentioned that C is a complete garbage? Probably, I probably have. So turns out that there is another corner case, is that if ptr is actually null, but new size is greater than 0, right? So they give you, ptr equals to null and new size is like, I don't know, 100 or something like that. Then you suppose, instead of freeing stuff, you're supposed to return a malloc of that new size. Why? Well, because fuck you, that's why, I guess. So yeah, or yeah, let's leave that login here. Yeah, so let's see, cargo build and then preload for ls. And yes, it works. It works now. So we are allocating, let's maybe disable some of the logging. Or, you know, let's keep it. So uname minus A works just fine. Oh, jeez. So allocating, freeing. I would expect more freeing action to be in place, but I don't know. Yeah, freeing. Okay, let's maybe try something like Lua A equals to 1, B equals to 2, A plus B equals to 3. So, and here we're, you know, we get to see all the allocations and deallocations that happen. During that, during that thingy. Yeah, I mean, it seems to be working. Although, like, I'm very much frustrated about this realloc shenanigan. Like, I really don't feel that this is a good idea to have like those corner cases, right? If like PTR is not null but new size is actually null, that we need to free this PTR. But if it is null but new size isn't, then this is just a malloc. I don't know honestly. But yeah, this is what you have, folks. C is garbage. Yeah, so let's try it out with Python, maybe Python 3. Ooh, lots of stuff. A equals to 2, B equals to 4, A plus B equals 2, 2 plus 4 is 6, freeing, allocating, that kind of stuff. Yeah, I mean, there you have it, I guess. And on the next video, we will try to play around with that concept a little more, maybe implement like a proper allocation strategy, kind of, you know, maybe like a linked list based allocator. I don't know, we'll see. And who's calling me? Jesus. Yeah, there you have it. And I'll see you on the next time. See you, folks.